To navigate a world of infinite information, the human brain must constantly synthesize thousands of isolated data points into a single stable idea. This cognitive transition frequently stalls during the middle school years. Educators identify grades 5 through 9 as a transitional black hole, where higher-order thinking often fails to expand. Adolescents in the United States currently fall behind other developed nations in advanced reasoning and problem-solving skills, marking a significant gap in cognitive potential. Much of this decline correlates with an educational emphasis on standardized testing, which prioritizes the rote retention of facts over the ability to solve novel problems. This model relies on a specific misconception: the assumption that basic fact mastery will automatically mature into critical thinking as the brain ages. Neurobiology suggests otherwise. Rote memory and abstract reasoning are independent cognitive systems. Mastering one does not trigger the development of the other. Strategic gist reasoning represents the neglected fourth R of education, alongside reading, writing, and arithmetic. This skill relies on top-down cognitive control, utilizing the brain's frontal networks to derive global meaning from explicit details. These frontal regions undergo massive structural remodeling during adolescence, creating a developmental window that is both highly opportunistic and uniquely vulnerable. Because gist reasoning is frontally mediated and biologically distinct from memory, it requires active training to emerge before this adolescent developmental window closes. Mapping how the brain translates raw data into meaning requires a specific theoretical framework. Strategic gist reasoning is the capacity to bind explicit details from different sources to form abstract, unstated meanings. This diagram shows the flow of that process, beginning with strategic attention. This filter reduces cognitive load by inhibiting irrelevant information and encoding only the most important details. The process moves into integrated reasoning. Here, the brain combines those explicit facts with pre-existing knowledge to construct an initial mental representation. When these facts merge with world knowledge, they produce a generalized meaning, a novel idea that was never explicitly stated in the original input. Finally, elaborated reasoning allows the individual to apply that meaning to new contexts, generating multiple abstract interpretations. This system functions as a bidirectional algorithm, using top-down verification to constantly update incoming details with higher-level concepts. Empirical neurobiology provides physical evidence for the divide between fact retrieval and meaning synthesis. In a study using fMRI and ERP imaging, participants judged statements based on either congruent gist or congruent detail while viewing complex digital images. Using a Norman Rockwell painting of a girl outside a principal's office, researchers compared a detail prompt, like "two adults are in the next room," against a gist prompt, "stand up for what you believe." This graph shows the event-related potential recorded during the trials. Between 690 and 1070 milliseconds, the processing lines for gist and detail diverge, indicating the brain handles these two types of information using different temporal signatures. Spatial fMRI mapping shows that identifying concrete details relies primarily on the bilateral superior parietal regions. This topographical map illustrates gist processing. The activity is concentrated in the frontal networks, confirming that synthesizing meaning requires different physical circuitry than recalling facts. Because the frontal lobes are actively remodeling during adolescence, the specific circuitry used for gist processing is uniquely sensitive to environmental disruptions. Examining clinical populations reveals how easily these frontal networks can be disrupted, beginning with traumatic brain injury. Youth with early TBI often experience a neurocognitive stall. They recover the ability to learn concrete facts, but fail to develop higher-order gist reasoning as they enter adolescence. The injury often damages axonal connections to the frontal networks, a deficit that only becomes apparent during the teenage years when those networks are expected to mature. We see a similar disconnect in students diagnosed with ADHD. When assessed on memory for explicit facts, students with ADHD perform at the same level as their typically developing peers. This chart tracks cognitive development. On the left, fact memory is identical, but on the right, the reasoning scores for students with ADHD, in light gray, plateau during adolescence, compared to the typical students in dark gray. Over-reliance on explicit details may strengthen posterior neural networks at the cost of the frontally mediated systems necessary for integration. In these clinical cases, intact fact retrieval masks a significant failure to synthesize those facts into deeper meaning. This stall in reasoning proficiency extends well beyond clinical populations. This graph compares reasoning proficiency in 8th graders. 84% of typical public school students, represented by the light gray bar, failed to meet the established criteria for abstract reasoning achieved by their private school peers. Education that focuses exclusively on standardized rote learning poorly prepares the adolescent brain for higher-order tasks. To address this, researchers initiated the Strategic Memory and Reasoning Training, or SMART program, in public middle schools. The protocol shifts focus away from what students are learning and toward the strategy of how to abstract generalized principles. This chart shows the results of the SMART trial. The black bar on the left indicates a significant increase in GIST reasoning scores after only 10 hours of strategy-based training. Students in the control groups, including those trained specifically in rote memory strategies, showed no significant improvement in their reasoning ability. The most significant finding, however, involved the students' memory for raw details. The black bar on the right shows that students in the SMART group matched the memory group in fact retention. By learning to synthesize meaning, they naturally improved their recall of the component facts. The data shows that top-down processing enhances bottom-up retention. This demonstrates that prioritizing synthesis is an efficient path to securing facts while simultaneously building higher-order skills. GIST reasoning is a discrete, measurable frontal lobe algorithm that can be significantly improved through targeted intervention. This cognitive system operates independently from the mechanisms used for rote memory. Focusing exclusively on fact acquisition leaves the adolescent frontal lobe understimulated during its most critical phase of growth. With facts now instantly retrievable through technology, a curriculum limited to data storage no longer meets the needs of a maturing brain. Failing to train adolescent reasoning results in a direct loss of national human cognitive capital. Corporate and medical leaders have identified a growing population of graduates who possess academic facts but lack the capacity to solve challenging problems. Securing our cognitive future requires moving educational goals away from simplistic answers and toward complex decision-making. We must shift our metrics from what a student can retain to how a student can synthesize.